Hello guys, welcome back to my channel. It's on African motives, still on engineering science and for. So we just want to focus in this case on statics, there where we are having the question paper from the paper of April 2021. So we just want to see how we are supposed to attempt that question, which was on statics, like I said. So we have got a question here where we are given a light beam which is loaded as shown in fig 1. So this is what we are given, guys, on fig 1. By referring to fig 1, determine the following: the reaction forces B and D. So we've got B and D, which are the reaction forces, which are the supports. All right, but there is something that is important here, because there is a distributed load. If we are to cross check here of 5 kilonewton per meter, so we have got this in between A and B, also between B and C. So between A and B it's 1 meter. So this is going to be 5 times 1, which is actually going to give us 5 kilonewton here. Remember, the force per meter times the distance. Then it is going to be separated between 0.5, because 1 divided by 2, that's going to give you 0.5, and also 0.5 here. Then between B and C, it is going to be 5 times 4, which is going to be 20 kilonewton. But it will be between 2 meters, because 4 divided by 2, that's 2 meters here, also 2 meters there. So what I'm simply saying, or what I'm simply representing here, is like this, guys. All right. This is how you are going to represent it. Take note, we had 5 kilonewton per meter, then 5 times 1, which is 5 kilonewton, between 0.5 and 0.5 to give us 1. Then between 4 meters, that's 5 times 4, which is 20, between 2 meters now. So now let us take our moments. So we shall start with moments about B, then we move on to D. All right, so that is what we have in this case, which is 5.11. So I'm going to start with to take moments about B. So taking moments about B, this is what you're going to have. As you can see, D going back to B is going in an anti-clockwise direction, this direction, that is anti-clockwise. So definitely we shall have the sum of the anti-clockwise moment being equal to the sum of the clockwise moments in this case. So you must visualize this in your mind. Okay, so this is D back to B, which is a distance of 4 plus 1, which is 5. So it's D times 5, which is 5D in this case. Okay, do we still have anything that is on the anti-clockwise as we are talking, or as we are referring to B? Remember, anti-clockwise, that is this direction. So I want you to see 20 is moving this direction, which is clockwise, clockwise, and also clockwise. But if you are to check, this 5 kilonewton is moving this way, which is anti-clockwise, and also 15, which is also anti-clockwise. So take note that distributed load on the left side of B, we shall have a 5 kilonewton between 1 meter. So it is going to be 5. So we have got 5 between a distance now back to B. So what is the distance between B and this force? It's going to be 0.5. So that's times 0.5 in this case, plus also we said we have got 15, but back to B it's 1 meter. So it's 15 and 1 meter. So that's 15 times 1, which is equivalent to those that are on the other side, which is now we are referring to the clockwise moments, which is 20 times 2. So I hope now when you have diagram like this, it's easier now. 20 by 2, so that's 20 times 2. Then you move on to another one, which is this 52, and there's a distance of 4 meters in between. So it's 52 times 4. That's 52 times 4. In this case, you move on, we still have 35 back to B, which is so this one is not 4. Okay, 52 and 4. All right, then we have got this back here at E, which is 35, and this is 4 plus 1, which is 5, plus 2, which is 7. So it's going to be 35 times 7, like this. All right, So we have to combine, which is going to give us 5D, then combine these two together. That is going to give you 17,5. If you add properly, that's 17,5, which is equal to, you combine these also together, that's going to give you 493. So definitely we have to transpose. That's 5D is equivalent. If you transpose this, that's going to be negative 17,5, which will give us 475,5. So if we divide by 5 both sides, that will give us D, which is equivalent to that's 95,1. That's 95,1, which is in kilonewton, because all the forces there, they are in kilonewton as we noted here. So that's our D here. So you can just write this as 95,1 kilonewton. So you can use sum of upward forces being equal to sum of downward forces, but just taking moments about D, we shall have our part like this. So also it's important that you just know this, how to take moments. Okay, so taking moments about D this time, so that we can have the support of reaction, which is the reaction support B. So at this time, as you can see, B going to D is going this direction, which is a clockwise direction. So that means we shall have the sum of the clockwise being equated to the sum of the anti-clockwise moments, which is B going to D. There's a distance of 5 meters, with 5 times B, so it's gonna be 5B. Okay, take note, we are talking of D in this case. So what else do we have that is still moving in clockwise? So as you can note, these all, they are moving in an anti-clockwise manner. So we are going to have this one, it's moving in a clockwise. This one is clockwise, which is 35 and what, and 2. So that's going to be 35 times 2, which is on the clockwise direction. All right, so we are done with the clockwise. We'll move on to the anti-clockwise. So back to D, we're going to start with this one, which is anti-clockwise, 52. Then there's a difference of 1, so it's 52 times 1. All right, then plus, we move on to, so in this case you can just distribute this in between, or you can just take it as it is, no problem, because already we have done it like this. So it's going to be 20 kilonewton back to D. So it's this, there's 1 meter here plus 2 meters, so it's going to be 3. So it's 20 times 3. Okay, that's 20 times 3. All right, we move on to this 5 kilonewton between this distance. But what is the distance now back to D? So it's, take note, there's 0.5 here, so it's going to be from this one to this one is 4 plus 1, which is 5. So we are at 5 now. Then 5 plus 0.5, take note, is 5 plus 0.5, which is 5.5. So it will be plus 5 times 5.5 plus also 15 back to D. So this is 156, so it's going to be 15 times 6, 4 times the distance. So you combine everything, so this is going to give us 70 here. Then if we combine this side, what are we going to have? This is 229.5. Then transpose this, is going to be negative 70 there. So if we subtract 70, that's 5D will be equal to 159. Okay, that's 159.5. Then we divide by 5 both sides. That's our D, which is going to be, guys, I'm taking, where am I taking? This is B. Yes, I hope someone saw this earlier. All right, so this is our B, not our D. So our B is going to be, if we divide properly, that's going to be 31.9, which is in kilonewton. So that's our B there. So we have got the reaction B, or the support B. All right, so let me take this. All right, this is our B here. We said we obtained 31.9 kilonewtons. So that's what we obtained here. All right. Anyways, so you can prove this by taking forces down and forces up. They must give you the same value. That is for you to see that this is what is actually correct. It's actually correct or not. Okay, so Let's move on to the other part now, which is asking us to draw the shear force diagram for this information that we are having. So the shear force diagram, guys, is going to be like this, because okay, let me just take this. Where did I put this diagram? I want to work with that diagram. Okay, so this is the diagram here. We are going to work with this diagram here. So in order for us to have the shear force diagram, we have to consider the forces, how they are being taken, and how we are moving. Okay, so this is it, guys. Let me just save my line here where I'm going to have it. So I'm just going to indicate the important points, how they are supposed to be taken. Like so, as you know, guys, definitely you have to start at 0 kilonewton there at ground. That is at 0. Then what happened is that direct at point A, there is a point load. As you can see, the point load is going down, and every point load carries a negative. So we're going to subtract minus 15 at 0. So that's 0 minus 15, which will give us minus 15 kilonewton. So this is going direct up to minus 15. It's a vertical line, a straight line up to minus 15 kilonewton. All right. Then what happened? We are at A. In order for us to move from A to B, there is a distributed load. As you can see, there is a distributed load in between. So this is going to be like this, a distributed. Remember, it will be slanting like this. So remember, we are at minus 15. That is where we are now. So we are going to subtract 5 kilonewton going downwards. So it will be minus 15 minus 5, which will give us minus 20 kilonewton. So this will go downwards up to minus 20. So we subtract that minus 5. So it will be like this. It's slanted like this up to minus, we said minus 20 in this case. So this will be at minus 20 kilonewton. All right. Then after we are at B now, at B, there is a support which is going upward direction. So we are going to add, because this one is an upward force, you add. So we are now at minus 20, then we add 31,9. So if we add minus 20 plus 31,9, this is going to give us something like 11,9 kilonewton. So this is going up to 11,9 because we are talking of a support. So this one goes direct vertical, just like a point load. It goes direct down. This one, it goes direct up. So it's going to be up. So you draw a vertical line with your ruler, guys. Okay, up to 11. Maybe let's just assume it's here. So with a ruler, make sure that you draw something nicer. So it's gonna be at 11,9 kilonewton. That is where we are now. All right, sorry, let's move on. We are now at B. Then from B to C, there's a distributed load for 4 meters. This one is still distributed. So we are going to subtract minus 20 because it's the one that is between these 4 meters. Where are we subtracting? Where we are now at 11,9 here. At 11,9, you subtract 20. So 11,9 minus 20. If you subtract this, you are going to obtain minus 8,1 kilonewton. So which means you are going down to minus 8, but this is a distributed load. And also minus 8,1 is below this line. This one, it's below this line, but it's below minus 15, but this is minus 15. So maybe it's somewhere here, we just assume, because it's not supposed to be under minus 15. So it's somewhere here. Let's say somewhere here, slanted line like that, because it's a disparate load here. So let's say that's where we're having our minus 8, we said minus 8,1. Yeah, minus 8,1 kilonewton. That's what we have. Anyways, we move on. We are now at C. At C, there's a point load which was directly given of 52. It's going down, it's a negative. So we are going to subtract 52 from where we are. We are at minus 8,1. So we subtract minus 8,1 minus 52, which is going to give us minus 60,1. So this will be minus 60,1 kilonewton. All right, so which means this one, take note, it's a point load, so it's going direct, it's a vertical line. Okay, it's not slanting, so it's just going direct. And also minus 60,1 is not supposed to be in within, because this is minus 20, so it's supposed to be down there under minus 20. So you draw a vertical line, maybe somewhere here, as long it is after minus 20. So this is supposed to be a straight line, a vertical line up to minus 60, we said minus 60,1 kilonewton. This is 1 kilonewton. All right, this is at what? At C. Now at C, you move to D. There's 1 meter between there, and there's no distributed load, so we just move a horizontal line, just a horizontal line, 1 meter. Then D, it's a support and it's a positive force, is going up, so you're going to add 95,1 to where we are at minus 60,1, because we are still at minus 60,1, because this is the same force throughout here. So you're going to add at minus 60,1, we add 95,1. So if we add 95,1, we are going to obtain 35 kilonewton. All right, so this is going up to 35, and 35 is above 1911,9, so it's going up there, but it's above. So let me just save it like this, above this somewhere here. All right, something like that. Okay guys, you see this issue of using a hand is supposed to be a straight, a vertical line. Anyways, I hope you understand the idea. So this is the point, it's a positive, it's above there. So that's 35, it's above 11, so that will be our 35, like that, kilonewton. Okay, so we are at point D. From D to E, there's a movement here, there's a distance between, so we're going to maintain a certain distance. There's no distributed, so you just move a horizontal line just like that. Then at E, we've got a point load which is going downwards, and it's supposed to be a negative, so you're supposed to subtract 35. Where are we subtracting? At this 35. So 35 minus 35, that is going to give us 0 kilonewton. So this will be at this point at 0, because remember, 0 in the horizontal, so this one is going to close up the figure at 0 kilonewton, like that. So that's what we have, guys. As you know, this is positive, negative, and negative, and we have the maximum bending moment when it crosses the horizontal line like that. But that is what is important. So shear force diagram, guys, is just taking the force. Is it going down? You subtract. Is it going up? You add. When it is a distributed load, that's where you have to indicate with a slanted line like that. But if there is no distributed load, you just draw a horizontal line. That's all about the shear force diagram. That's all about the shear force diagram. Just that. So anyways, that's it. Let's see the other question that we had in this case, which is to calculate the coordinates of the centroid of the lamina. So in this case, we need the coordinates of the centroid there of the lamina in this case. Okay, so actually there are so many ways and methods that we can actually use. When I say ways and methods, what do I actually mean? I'm just saying that if we are to cross-check, because we are working with a centroid in this case, so to calculate the coordinates of the centroid, definitely you have to work with the area moment. So which means you're working with areas. If it is the center of gravity, you are working with what? You're working with the volume. All right, anyway, so there are two ways that we can do this. This is it. We can have our figure like this. Let me just put it this way, maybe it can be clear. We can have our figure like this, where we have got the shape, the shape that we are having, then the area, then the centroid. So in this case, we are talking of the shape, which is the triangle. As you can see, the bigger shape is a triangle. Then you've got a square, because this is 14 millimeters. This is also 14 millimeters. So this is a square. because the sides are equal. All right. So what you're going to have, we are going to calculate the areas. Like I said, there are many ways of doing this. Okay, but as for this one, let's calculate the area. We know that the area of a triangle actually, that's half base times the perpendicular height. So in this case, we are going to have the half times the base of the triangle, which is the base from this point B to C, that's 75, times the height, which is 55. So it's half of 75 multiplied by 55, like that. All right, so this is what you're going to have. So if you multiply properly these two, you are going to obtain an area of 2062,5, which is in square millimeters, but those were millimeters. So this is our first area. Then, so we just put this as our A and our centroid as our C. All right. So we are going to find the centroid of the triangle, and take note, in this case we are calculating the coordinates. That is, we are working with both. We are working with both. We are working with the x value and the y value. So which means we need to know if it is a triangle, it's going to be a third base and a third the height. All right. So which means the value of x is going to be a third times the base. Okay, that is the value of x, which is a third times the base, which is x, and this is y. And the value of y is going to be a third times the height. So the base in this case, remember the base is 75 from our triangle. So a third of 75 is going to give us 25 millimeters, and that's our x here. Then our y in this case is going to be a third times the height, which is 55. So a third of 55, which is going to give us a decimal, which is 18,33333, so on, which is going to be 18,33. That's millimeters. All right. So okay, this is what you were supposed to actually do in this case. You were supposed to calculate the total for the two in this case, because you are working with the area moment in this case. So you've got the area moment that is going to affect the value of x. Okay, then you are going to have the area moment that is going to affect the value of y, like this, guys. This is what I'm going to just extend my diagram like. We have got for the triangle, we have got the area moment that is going to be AC, that is our area moment. Okay, so we've got the area moment for x and the area moment for y, for the y value. So we are going to have the one for x, which is going to be that's going to be area times c1, which is in this case our x1, which is 25. So you're going to multiply the two, because here in this case we are given the two. We have got the distances between the two, so you simply need to multiply these two for x. All right, so that's c1, which is the value of x. So let me just write it as x1. So it's going to be, you multiply this to this. All right, so you're going to obtain 5, 1, 5, 6, 2, comma 5. So this is area moment, which is a cubic units. Okay, so this is for x. All right, this is for x. Then you find also for y, which is a1c1 for y this time, which is going to be area times the value of y. Okay, which is the area, which is this one, times the value of y. All right, so you have to multiply those. So this will give us for the y now. So multiply this and this value properly. You're going to obtain, that's got the 37811. So actually I'm going to have another method that I'm going to use also to calculate this. All right, so this is it here. Let's see. So these are like we are having our area moments here. So these are like the area moments. We are calculating our area moments. Okay, this for y, and this one we are calculating for the x values, for the y values, that is for the triangle. Okay, then we shall calculate the total later on. Then we move on to the square. So like I said, I've got two methods that I'm going to use. For the square, this is what is going to happen. Remember that for a square, area is equals to side squared. So that is the side that you're given squared, which is b squared, and we are given a side from our shape here, which is 14 millimeters. So that's 14 millimeters, 14 millimeters. So it's just going to be 14 times 14, or 14 squared, which is 196 square millimeters. All right. Then for the centroid, which is in this case, a square is just going to be b over 2. They are just the same because it's either the same. So it's 14 over 2 over 14 over 2. So our x is going to be 14 over 2, which is actually 7. Yeah, that's 7 millimeters in this case. All right, then our y is going to be also 7 millimeters because it's just the same. All right, so just like what we did on the triangle there to calculate the area moments, that is what we are going to do also. We calculate our area moments. So the area moments is simply the product. Okay, so this one, it was for the triangle. We move on to our square. So for the square, we shall have for x again the area moment. This time we shall have it as a2. So it is going to be a2 c2. We are multiplying a and c2 for x, the area 2, and this is your centroid 2. So it's area times the x value for x. So it's 196 times 7, 196 times 7, which will give us the area of 13. So this will give us 1372, which is a cubic millimeters, but this is area moment. You move on for y, you do the same. For y, you multiply area times the distance for y. So as you can see, these two are the same, so you shall obtain the same value for y, which is 1372 cubic millimeters. So I shall show you another method again. So why am I calculating the area moments? It's because we know that the value for x there is just going to be the sum. You add the values for x. Okay, this is what you have. But in this case, take note that the square is inside the shape. Let me bring back the diagram here. This square is inside. It's like a hole. Whenever you're having a hole, you subtract that. So you're going to subtract the square. Okay, so in order for you to have the total areas, okay, so let's start. Okay, we have the values for x, that is the total moment, but working with that part that was with x over the area. Okay, the same with y, you calculate the total for the area moments for those ones where with height of y, then over the area. But this area, all these are going to be affected by that square because there is a square that you subtract. Okay, so let's start with the total area. Okay, so the total area is easy, guys, because we are simply subtracting these two, because we have got a triangle which is like this, then a square inside. So you subtract a square from a triangle, so it is area 1 minus area 2, area of a triangle minus area of a square. So you're going to subtract this value minus this value, which is going to give you something like 18, because you are subtracting 20,5, this one minus 196, which is going to give us something like 1866,5, which is in square millimeters. So that's your total area. Then we calculate the total moments now here, but you work with x first. We work with x. Okay, so we are going to start with those ones for x. So the total moments for x, we do the same. You subtract the total, the area moment that you obtained for the triangle for x minus the one for square for x, and we have them here. We said the total area moment for x here, when we are taking x values, this was the total area moment for a triangle. Okay, so for x for a triangle is this one, x for a triangle, which is 51 562,5 minus the 1 for a square, so for x, but you're working with x values only, so for a square it's 1372, which is going to give us that's the total for x, which is 5. So it's going to be 553,5. Okay, this is area moment, which is cubic millimeters. All right, you do the same for y. Okay, you calculate the total area moments, which is still the same, the triangle, the total area moment for a triangle, but working with y values minus a square, because a square is a whole, so you subtract it. So it's this one minus this one, so it's going to be 37811,8125 minus this one for y, which is the same as for x, was a square. So this one is going to give us 36439,81 okay, something like that. So that's what you're going to have, 25, something like that, which is also cubic millimeters. Okay, so why are we calculating this? Because remember, we said in order for us to have the value of x, we are going to calculate the sum of moments for those ones which are having the x values, which is this one for x, which is this value here for x, which is going to be 514,253,5 divided by the area, and our area is this one for both, it's 1866,5. all right, so if we divide these two, that is for x, we are going to obtain something like 24,335, then that will be millimeters, because these are cubic millimeters, this is area, which is in square millimeters, so the answer is going to be in millimeters. You do the same for y, total moment for y, which is the total moment, which is this one, 3 whatever that you have, 6, so it's going to be 364,39,812 and so on, over the value of the area. The area is still the same, 1866,5. all right, and this will give us the value of y, which is 19,523, which is something like that in millimeters. So take note, this is a point of x and y, so remember it's going to be written as a point, which is 335 19 that's going to be 19,523. all right, something like that. So this is our centroid, because the question was asking us to calculate the coordinates, which means you're talking of x and y of the centroid. So take note, when there is something like that, you subtract. So that's the concept there. So like I said, we could have done this in another way. Let's say we wanted to use from this diagram here, from this table here, we could have just taken moments from that part. If we want to calculate the value of x, you work with moments about the x. So remember, that is what you do. Okay, so this is what I'm going to do. I'm going to take moments as another method to calculate these same values that we did. So you choose which method is best for you. So if we are to take moments, we are going to say, let's start with moments about the x-axis. Moment about x-axis. If you are referring to moment about x-axis, which means you are going to calculate the value of what? Of y. But take note, these are moments about the x-axis, so you're going to calculate the value of y. You use y values for that. You're going to use y values. Okay, so remember how you calculate moments, that the total moment must be equal to what? The total moments should be equal to sum of what? Of separate parts, of the separate parts of moments. So you're going to add the sum of the separate parts. So the sum of moments, we are saying that it's area times the distance, which is y, the one that you want to calculate. But now the area times the distance that we are talking about in this case, which is from force times distance. So we are saying this area in this case is the total area. All right, so we are going to have the total area times the value of y, which is equivalent to the sum of separate parts, which is the area moment of what? Of a triangle. Okay, so this is going to be the area moment, which is going to be the area of a triangle times the distance that we are given for y for that triangle. So you're going to use this y value for, which is y1. So let's just say a1 y1 so that it can make sense. A1 y1 like that. But take note, guys, take note that the square is inside the triangle, so you subtract for the square, which is a2 y2. So that's the concept. So this at we said is the total area, where we said at is equivalent to a1 minus a2. Why? The square is inside the triangle, so you subtract, that's a1 minus a2. All right, so that's your at. So you're going to subtract, which is these values, 20 62,5 minus the area of a square, which is 196. You subtract these two, multiply by the y, which is the value that you want to calculate, is equal to area 1 times y1, which is area 1 times y1, which is 18. So you multiply this by 18, which is going to be 20. 62,5 multiplied by 18. This is 18,333. Okay, that's it. Area moment for the triangle minus the area moment for the rectangle, which is 196 times 7. So you multiply 196 times 7. Just like that, you can even obtain the value of y. So you simply divide by this bracket of 20, 62,5 minus 196. Both sides, you can have the value of what? Of y. So by doing this, you can actually obtain the value of y, which is going to be the same as the one that we obtained, which is 19,523 millimeters. All right, so that's another method that we could have taken. So here we used the moments about the x to calculate the y value. So you do the same, just like what we have done, but it's now about the x, now about the y. So we are going to take moments about y-axis, so which means we are going to calculate the x value. So this time you work with the x values. So these are the ones that you are working with now. So the formula is still the same. The total moments is equal to the sum of what? Of the separate part, but this time you're working with x. So it's going to be the total area, but this time it's affected by what? It's affected by x. It's no longer affected by y, just like what we had. All right, so this is what it's going to look like. Okay, so I'm going to take the area, total area, times x, which is equivalent. Now the sum of separate is area 1 times x1 this time. Area 1 x1 minus area 2 x2. So remember our total area, guys, we said that one, you simply subtract the two, so it's just going to be the same as the one that we just did here, which was 20, whatever that one is a repetition. 20 62,5 minus 196. X is equal to a1 times x1. It's a repetition, guys. Now it's a1 x1, so you're going to multiply this area 1 times x1. This is your x1, so it's 20 times this, 26,5 times 25, which is your x1, minus area 2 times x2. So this is your x2. So this one is just the same as the previous one, 196 times 7, because these ones, they are having the same answer. So in order for you to calculate x, definitely what am I going to do? To divide with the bracket, 5 minus 196. You divide also here, which is 20, 62,5 minus 196. So definitely this will cancel. You've got your value of x. So that is what you're going to have, which is 24, 335, which is in millimeters. So definitely as a point as xy, you do like what we did in the previous question, where you have to write this as a point or as coordinates. So guys, as you can see, if you are working with the statics, that's how they ask this question about the centroid. It can be the center of gravity, it can be the centroid, but the idea there is the same. Are you working with a figure where like you're having maybe a rectangle, then a triangle on top, like that? This one you have to add. Okay, so it's area 1 plus area 2. You add, that will be your total area 1 plus area 2. But on a condition where you are having a certain shape or a certain figure inside a certain shape, this one is your area 1 and this is your area 2. Your total area, you're going to subtract area 1 minus area 2 whenever there is a condition like this, where you've got a figure that is inside a certain figure. You subtract that. So please take note, guys. But when you are given such type of a question, maybe it's a rectangle here combined with a triangle, this one you add, nothing is in between, so you just take as it is. So that's it, guys, for Meson African Motifs, working on engineering science, and for till we meet again.